Hello, I'm here today with you to help review some of the older topics that are covered on the AP Calculus exam for BC. And so we're going back to your math analysis or your Calc 1 or your Calc AB days and reviewing some of the oldie moldy things. In addition to that, we will touch on parametrics and in general particle motion, as well as on limits involving L'Hopital's rule. Okay, so I'm not going to go through every question that is on this video handout. However, I will show answers for everything that's in this video handout. So just understand that the video would become quite long if we did every single problem here together. So we're going to start out with doing number 1 as an example. So if you were to just direct substitute, which is and absolutely should be your first thought with every limit question, can I just substitute in this case, 0? Would that work? And it would not, because this is a situation where we have an indeterminate form. Please remember that on the AP exam, we need to write out the reason that we can use L'Hopital's rule, and so we need to think about the limit of the numerator, the limit of the denominator, and in this problem, both of those are 0. So we're going to say that L'Hopital's rule applies because we have an indeterminate form. Now, in referencing the indeterminate form 0 over 0, make sure you do not equate that to the question at hand, because you're about to evaluate that question, actually find a value of it. And if you say that the value that you get, spoiler, the answer here is pi. If you were to say pi as an answer and then also equate that somewhere in your work to 0 over 0, you're saying something that's mathematically false. So that's why we try to write those 3 bullet points with limits completely separate. We're just trying to avoid that error, that linkage error. Okay, so L'Hopital's rule says if I have an indeterminate form of 0 over 0 or some kind of infinity over, plus or minus infinity, then I can take the derivative of the top and the derivative of the bottom, and the limit of that result will equal the limit that I actually began with. So here are my derivatives of numerator and denominator, and I'm very excited because now my denominator is 1 instead of 0, so that looks promising. And if I think about this for a second, I personally would rather not have secant involved, so I would just rewrite this like so, put cosine of pi x squared in the denominator. That's a personal preference. You do not have to do that, but in thinking about what happens as we look at cosine at 0 is 1. And so I'd have 1 squared in my current denominator, which is how I get the answer of pi. Okay. Now I do have number 2 worked out. Number 2 is also a L'Hopital's rule. If you would like to pause the video and work that question yourself, I would recommend it. And I will just show the answer for this in a second. Okay, so here is the work for number 2. You can see in my pink pen that I have written out my bullet point justification. Then I have gone ahead and taken a derivative of the top and the bottom since I had an indeterminate form 0 over 0. Now this step right here is a personal choice kind of situation because there's a lot of ways to think about a trig function. And so over here, I just chose to rewrite things with sine and cosine and so on. You may or may not have made that same decision. So your intermediate work might be different. I applied L'Hopital's rule a second time. I would, if it were my AP exam, write those bullet points out a second time. College credit is worth it. And then eventually I get to the juncture where that limit evaluates to 1. So completely different paths are possible in the middle of the question there. I do think you'd get to this point with the green check mark, and I hope you got to this answer, okay? The middle part might differ from person to person because there are different choices you can make with the trig. Okay, so let's take a look at this next one. Question number 3 is one of the bad indeterminate forms. I have a base that gets infinitely large with an exponent that gets infinitely tiny, approaching 0. Infinity to the 0 is a bad indeterminate form. It needs to be manipulated to become a good indeterminate form on which I can use L'Hopital's rule. So we're going to make a statement, and introduce a new variable. We'll call it y. So let y equal the argument of our limit statement. And then we're going to take natural log of both sides of this, which will allow that exponent to come down in front. And then what I'm really hoping for, bear in mind your goal, is to try to find something that is a quotient. So I can try to look at a 0 over 0 or infinity type over infinity situation. Okay, so I have something like this. Instead of thinking about the limit of y, I am instead going to think about the limit of natural log of y. So be cautious, do not write an equal sign between the given problem and what I am currently writing in green. They are definitely not equal to each other. Here, this is my thought cloud would be this is the limit of natural log of y. The original question is the limit of y. Those are not the same thing, okay? They're related, which is what I will utilize at the end, but they are not equal, okay? So do not equate. All right, so here I am with my little green problem here. And if I'm approaching infinity, I can tell that the limit of my top part is going to be infinite because natural log of x is this function, and it slowly grows towards infinity, very slowly, but it gets there, so to speak. Math jokes. This is also something that goes to infinity as x tends to infinity. Therefore, I can use L'Hopital's rule. Okay, if it were my AP test, I'd write that as a sentence format, right? I have an indeterminate form, therefore L'Hopital's rule applies. Here I am applying L'Hopital's rule now. So I'm going to take the derivative of the top, derivative of the bottom. This is the limit of 2 over x as x approaches infinity, which itself approaches 0. And now I need a concluding sentence. Since the limit of natural log of y equals 0 as x approaches infinity, we could deduce that the limit as x approaches infinity of just plain y is going to be e to the 0. It's this exponent on an e because this was based on natural log, and that answer will be 1. Okay, so the last 3 questions basically reviewed all the key ideas of L'Hopital's rule. If you glance back, questions 1 and 2 reviewed the idea that you need a 0 over 0 or infinity over infinity situation in order to use L'Hopital's rule and reminded you of the importance of the 3 bullet points. Question number 3 reminded you that there are other indeterminate forms that involve 0, 1, and infinity in various places. And if you have one that isn't of the easier form, you need to get it to be such that you can just directly use L'Hopital's rule. All right, question number 4, blast from the past. Okay, here we are with the nice green grass of spring. And we have a location down here. There is an airplane flying overhead. And there's an observer at the ground. And that observer knows that this airplane is above them at an altitude of 3,000 meters, also known as 3 kilometers, because I can see later on they're mentioning kilometers. And the speed at which the airplane, this is my airplane up here, moving along this trajectory, okay? So the airplane has a speed of 480 kilometers an hour, passes above the observer. On the ground, how fast is the distance from the observer to the airplane increasing? Okay, so and 30 seconds later. So 30 seconds later, the airplane's going to be over here instead of directly above the person. So this is the distance that they're talking about. And let's call this side A for airplane. Okay, now because it said that the airplane was flying horizontally, this yellow side is fixed, okay? It is always like the airplane is staying level as it moves across our picture here. So that can permanently be in our equation. This is a related rates question. And so we're going to say here that a squared plus 3 squared equals d squared, which means this would be my related rate statement. Okay, we can divide everything by 2. This side was 0 because it's not changing, so the rate of change would be 0. And then there was mention here that the speed was 400 kilometers an hour. So d/dt is 480 kilometers an hour. Okay, and then it mentioned something about 60 or 30 seconds later. So we would need to do a little bit of, believe it or not, factor labeling here, and say if we have 480 kilometers an hour has 60 seconds, and there's 1 minute. Oop, did I think about... I just did that wrong. Got ahead of myself. I was thinking about seconds already. 1 hour has 60 minutes. There we go. Factor labeling wasn't working there for a minute. I had a panic. Okay. So this is going to give us the rate of the plane in kilometers per second. And then we have 30 seconds. Okay, so I don't have quite enough room here, so I'm just going to work this out. This is 0.13 repeating kilometers per second. And then it said 60 seconds had transpired, so we could take that result and multiply it by 30. And that's going to tell us that in 30 seconds, side A is going to be 4 kilometers. Okay, so this A side isn't always 4, but the moment that we care about, A is 4. Okay, so we could substitute in, if we think about that moment, if this is 4 at some moment and this is 3 always, at that particular moment that we're interested in, the D is a 5. Okay, so now plug in the values that are only sometimes true. The things that were always true, like this 3, could be there from the beginning. But the other things in the question that are only true at a certain moment in time, they have to be substituted in after you take the derivative. So here we'd have 4. Oh my gosh, I cannot write. Try that again. Here we'd have a 4. d/dt is 480. And because that side is increasing, that's a positive rate of change. Then we have our equal sign. And then, oh, I missed something back here a moment ago, didn't I? Have you been panicking this whole time? There was another d there, right? The derivative of d squared is 2d dt. Hoi! Okay, this is going to get you guys all excited when you're watching this video that I made a mistake there. It was because I chose D. That really was just, crazy on my part. Okay, so then we'd have 5 here, and then we don't know d/dt. Maybe I just like saying d/dt. What do you think? Okay, if you do that arithmetic, you should end up with the rate of change in that diagonal side being 384. And our units would be kilometers per hour. Is it? Or is it kilometers per second? I have to think about that. Okay, down here, I think when I was doing this myself, I wrote kilometers per hour, but now I'm thinking maybe it's kilometers per second. 480 was in kilometers per hour. Oh, well, maybe it's in kilometers an hour. Yeah, it's in kilometers an hour. Okay, moving along. Okay, question number 5. Question number 5 is a good old, what am I trying to say? Parametric. Goodness. And it does say calculator active. And we snipped this question from somewhere else, and we kept this in the stem, but we took off the part that actually utilized it. So you don't need that sentence, FYI. Okay, so here they're mentioning velocity vector. Vector, remember, just means that it's giving you information in components. So it's giving you the x portion of the velocity and the y portion of the velocity. Because it's a calculator active question, I would recommend that you put your settings to match the question, just to make sure that you're clear on things, okay? So for part A, it says find all values of t at which the tangent to the path is vertical. Slope is this, which is really in parametric context, dy dt over dx dt. Vertical means that you have an undefined slope, so we would need this part to be 0. So dx dt equals 0, and at the same time, we would need the top not to be 0. If you had 0 over 0, you'd have a cusp or something like that. That's not the same as having a vertical tangent line. okay? So really, this is just now a calculator question, so I would need to have this part set equal to 0 as the thing that I want to solve with my calculator. You could put this in your y1 and this in your y2, or you could move the 3/4 back over, right? Have this and then look for intercepts. I really don't care. All right, you do not need to be in parametric mode for this because you are just trying to solve an equation. And so solving an equation is something you can do in rectangular mode. And you can see down here the two answers that I got were 1.997 and 2.331. Okay, it'd be worth a second of just double checking that neither of those numbers, when substituted into dy dt, gives you 0. They do not. So we're fine. Okay, acceleration vector is basically just saying keep in components. Okay, and then think about acceleration. So we are given velocity information, so the derivative of the given would give me acceleration. Okay, the derivative of the given evaluated at 2, I should say. So this is the first thing I wrote down just as a notation to myself. And then I can have this in my calculator and use the nderive tool, evaluated at 2. Same thing here, use nderive, evaluated at 2. And I got these numbers. I hope you did too. Okay, that is just a calculator skill check, essentially. Okay, the last bit is a formula, okay? The speed equation, if you recall, has a big square root. It has dx dt squared plus dy dt squared as the equation for speed. So we're just going to utilize that, right? It just asks us to find speed at 2. So I'm going to show you that down here. Okay, plug in 2's for everything. That's a t, and sort that out, okay? So that's the value I got. I hope I plugged that into my calculator correctly. Please let me know if I did not. Okay. All right. Number 6, I'm not going to actually work out, but I am going to just briefly talk about it while I show my work here. So this is really going way back. It is, I liked having this next to the parametric so that you could see you did do particle motion in the class before we all met. So here, this is just really looking at, here's my equation. It says we have a particle moving along the y-axis. So I always imagine a knitting needle with a little bead on it. Okay, sliding around. Right, so you have this thing and it's moving up and down, sliding about. And the way that it's moving around is based on this equation. Okay, so that's a position equation. Acceleration would therefore be the second derivative, and evaluating that at 3. Velocity would be decreasing if its derivative, if velocity's derivative is negative, and so we check that. And then speed decreasing, part C, determine if the speed is decreasing. This is a question there you have to pay attention to the words here. Remember that speed is decreasing if velocity and acceleration have different signs. Speed is increasing if velocity and acceleration have the same sign. That's basically all it is. I believe in our notes way back in the fall, this was referred to as the Prius principle in Mr. Covey's telling of his quarter-life crisis or something like that. He likes to gloat that he's so much younger than me. It's really sad for me, maybe for him too, to be so young. Oh my goodness. Okay, this next set of questions, this next few are kind of quick, but all important. Okay, so number 7 is just basically reminding us about how to write the equation of a tangent line, to be honest, but just also not to freak out, okay? Because you look at this differential equation and it looks scary. You have to tell yourself to stay calm, all right? And it also mentions that there's an initial condition. The initial condition is just giving me a point that's on F, and I want to write an equation for a tangent line. Anytime I want to write the equation of a tangent line, I need a point and a slope. And I've already got a point. That's awesome. Okay, so I just need a slope. How can I get a slope? Oh, look, here's an equation for slope. That's what dy dx means, slope. Okay, so I'm working on finding that slope. So my slope is going to be dy dx evaluated at -1, 1. Notice my notation there. I think that is a really strong notation. I encourage you to use it. And my slope equation's right here. So that is inverse sine of, now I'm going to plug in my numbers. So negative 1 squared is 1 minus 2 times 1 is 2. And so I've got the angle whose sine is negative 1. And I know arc sine is restricted to this side of the coordinate plane. And to have all the angles go in order, I'd have to go from this juncture on up. So this is negative pi over 2. This is an angle of 0. This is pi over 2. And so the angle that has a sine value of negative 1 would be down here. And so that my angle there is negative pi over 2. Winner chicken dinner. Okay. So there's my slope. And then I needed to write the equation of a tangent line. So y minus the y value, slope x minus the x value. Every now and then I get this weird kind of answer on a tangent line problem where someone puts the equation of the derivative right here. So in this problem, that might have looked like this. This is full on wrong, you guys. Full on wrong. This is not a constant slope. That's an equation for the derivative at different locations, okay? So if you're being asked to write the equation of a tangent line, that's not it. That's not it at all, friends, okay? Because a line has to have a constant slope. All right. If you didn't understand that comment, don't worry. That must mean you don't make that mistake. All right, question 8. So this picture is of f double prime. I would write next to it that this is f double prime. It's easy to lose track of what you're looking at when you're thinking about something else, okay? And then we want to know when f prime is decreasing. If something is decreasing, that means its derivative is negative. So if f prime is decreasing, then f prime prime has to be negative, or f double prime has to be negative. Now notice this construct that I had. I could have put anything in these blanks, right? If I wanted to know when m of t is decreasing, I would need to know when m of t prime is negative, right? It doesn't matter what the label is in these pink words, right? For anything that would be true. If something is decreasing, its derivative is negative, okay? So this question boils down to, where is f double prime negative? You guys, we've got a graph of f double prime, and it's in negative land right here. So that's this chunk. Now you might wonder why that's a closed interval instead of an open interval. That's one of those math fights, okay? There are math fights about whether you should use open or closed intervals on increasing and decreasing and on concavity. And do not worry your head about it. I understand both perspectives. It's not worth our really discussing it. The AP is not going to get persnickety about it, right? You would never have a multiple choice that had both open and closed interval choices. Like on this question, they would not give you an answer choice that was this. So you had to deliberate, okay? That's not going to be the case. They're aware of the math fight. So use what kind of brackets you feel, okay? All right, this one. This is a very nice little question, okay? Nothing about it is especially hard. You just have to keep your head, okay? So here, they're just asking which of the following has the largest value. And I'm looking here at choice A, and it's talking about f prime at A. Well, f prime at A would be the slope of that tangent line. And so that looks like it is like some kind of a negative number. Slightly negative number maybe, okay? B says f double prime at B. Well, second derivative information, this is the original function. Second derivative information would be about concavity, and this is concave down. So this is also a negative number. And so far we've got two negative numbers. Interesting. F of C is 0. I can see that on the picture because that is a point on the axis. And then the last guy, this part of our graph looks to me just ever so slightly concave up. And this is asking about the second derivative's value at this location over here. And so I would say that that bit has to be just slightly positive, and it was asking me for the largest value. That one's the winner because a positive value has to be bigger than 0 or any side negative number. Okay? All right, the last one I thought I would just scroll through. Oh, this is my tidy answers. I thought I would just scroll through this one. It's important here to recognize that this is a picture of f prime, that this equation only works for the part of the graph that I am highlighting in purple right now. Guys, really bad drawing. How do you guys survive my drawing? You should get an award at the end of the year. Okay, for crap drawing that you have to interpret in my room. Okay, that didn't help. All right, so that side is this bit, okay? And then this chunk is based on a parabola, okay? And so here's our parabola equation. It is very important that you remember that this is where x equals 1. So depending on which part of the question or which part of the function you're interested in, you have to think about the appropriate f prime. Okay, f prime to the left of 1 versus f prime to the right of 1. That's one of the trickier things here. Okay, you're also given an ordered pair that's on function f. This graph is not function f. This graph is f prime. Okay, so let me just scroll down. Notice here that this is calculator active, so you'd get to utilize your calculator. Okay, I will briefly talk about this. So in part A, feel free to pause if you want to work this first. I think that would be best. I should have said that. Okay, but in part A, you're looking for points of inflection. A lot of times people have in their head a point of inflection is where the second derivative is 0. Please flush that from your brain. That is part of how you seek points of inflection, but the actual definition is a point of inflection is where concavity changes. So you need the second derivative sign to change. So we are going to look, and you also need to have a point, okay? So that would change the concavity, but you also need to have a point on the original function. You can't have a concavity asymptote, for example, okay? So we would have points of inflection at 1 and at 2, because that is where the derivative of the given graph will change sign. Notice the derivative speak that I have over here. You would have beautiful, beautiful words, right? Things like this that you would include explaining either side of 1 and either side of 2, okay? Be very elegant in the way that you talk about that. Okay, then I utilize some algebra and my calculator to find out that the point that I've labeled capital A has this decimal approximation. And the chunk of the graph that I have highlighted in blue on this screen is where f is decreasing because that's where f prime is negative. Part C is an involved candidates test, okay? In order to know the values of the function at the endpoints and at the relative minimum, you need to use fundamental theorem of calculus and that initial value of 0, -2 that was given right here. Okay, so I'm showing my work here. I don't know if that's the best way to show my work, but it is a way to show my work. And the last one's a little spicy because you do have to change. You can't just integrate from 0 to 2.5 because the definition of f prime changes over. So you need to go from 0 to 1 and then from 1 to 2.5. So that's this part of the work down here. That's a little bit longer. My values were the 3 values in blue. And since we were looking for a minimum, I chose the smallest one. Okay. So that is a brief overview summary of the topics that were listed at the top, reminding you of the calculus you did before we were in class together, reminding you of parametrics and how things are kept in component form, the speed increasing, decreasing, boiling down to looking at signs, the speed equation, that the word vector means to keep things in components, and then we also talked about L'Hopital's rule. Okay, you've got a few more videos coming up, but for the next couple days, we will try to focus most of our attention on these elements just to reinforce. Thank you so much. I appreciate your hard work on this.